Hi everyone, and thank you for attending today's webinar on how to use NVIDIA's DeepStream SDK and Transfer Learning Toolkit to deploy streaming analytics at scale, hosted by Nick Becker. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets. All of the widgets, as well as the slide area, are resizable and movable, so feel free to move them around to get the most out of your desktop space. If you have any questions during the webinar, please submit them through the Q&A widget. We'll try to cover as many as possible during the Q&A portion, but if there's any we don't get to, please post them on the forum to keep the conversation going. Be sure to check out the resource list for links to the developer site, forums, wiki, and more. And if you run into any technical issues during the webinar, you can always find answers to some common questions located in the Help widget at the bottom of your screen. An on-demand version of the webinar, as well as the slide deck, will be available approximately 1 day after the webinar and can be accessed using the same audience link that was sent to you earlier. And with that, let's get started.
All right. So today we're going to be talking for about 45 minutes about how to use NVIDIA's DeepStream SDK and Transfer Learning Toolkit to effectively deploy streaming analytics at scale. So as a brief agenda, we're going to cover several topics. We're going to begin by sort of talking about real-time streaming for video analytics in particular, and sort of what that means. We're going to then describe a standard common framework for analyzing video that is fairly ubiquitous across many applications. And then we're going to move into DeepStream. We're going to talk about what is DeepStream, and in particular what's new in DeepStream 3.0, which is our most recent release. And we're going to go into some example applications to show you some examples of what's possible and what's actually easy to build with the DeepStream SDK. And we're going to conclude by talking about NVIDIA's new release, Transfer Learning Toolkit, which makes it easy for developers and domain experts to get up to speed building state-of-the-art models, leveraging pre-trained models that they adapt to their use case. So to begin, we're going to talk about video analytics. The DeepStream SDK is a general-purpose streaming analytics framework for you to build applications from all sorts of sensors. But as video is one of the most ubiquitous sources of sensor data, it's a great place to begin. Cameras are everywhere. In fact, there's a recent estimate that there will be about 1 billion cameras in use globally by 2020. That's an incredible amount of raw sensor data. And with that data, people, organizations, companies are building incredibly powerful applications. Cameras are used, and streaming analytics are used for things like access control at airports, for managing operations in manufacturing centers and factories, doing things like parking facility management, effectively building the traffic and consumer flow applications that will power AI cities. Retail analytics is another great use case that's becoming more ubiquitous, where stores are trying to understand when people are looking for an item that they can't find in an aisle, or perhaps even building stores that don't require you to check out at a cash register in the case of the Amazon store. There's many other use cases that go into nearly every industry, but all of these are powered at the core by video analytics. And to empower people to build these kinds of applications, to power rich insights, we built a platform that we call Metropolis. It is an edge-to-cloud ecosystem that brings hardware and software together to help you build intelligent video analytics applications. It relies on the NVIDIA hardware and software ecosystem to allow you to build one application that you can deploy at the edge or on-prem or in the cloud with the same application. At the edge, it leverages the Jetson family of products, whether it's the TX2 or the Jetson AGX Xavier, as well as on-prem deployments can be leveraging the Tesla ecosystem, the V100 lines of accelerators. In the cloud, you have the full suite of data center capabilities. And all of this can be powered from the same application, so you have to build once and can deploy everywhere. And the reason that we did this is that we realized that there's a common framework for analyzing video across many applications. And we've put that framework on this slide. Across all applications that rely on video analytics, pixels coming from a camera, whether it's a network video recorder, whether it's coming from disk, will need to be decoded. And once they're decoded, they're likely going to have to be processed in some way before you can run any kind of intelligence engine to extract information from these pixels. That pre-processing might entail things like de-warping or orthorectification or scaling or just other types of rotation. Once that's done, inference is the next step. Things like doing object detection, tracking, classification, feature extraction, getting the insights out or creating the insights from the pixels. And once you have that, several things can happen depending on the use case. Information might be aggregated and then perhaps displayed back on top of the original pixel data in a composite output feed and then sent to a local display. Alternatively, or perhaps in addition to, that data itself, that raw feed, may have to be re-encoded so it can be persisted on disk for later analytics and additional storage. And that information that's been created also may just need to be passed through to a data analytics backend, whether it's for stream and real-time processing or batch processing that can be sent to additional users who need to rely on that information. Because all intelligent video analytics applications map to this type of framework, it means they're all sharing components. Decoding, preprocessing, encoding, data transfer, inference, all applications will have to build some kind of system to handle these things. And that's not what development teams want to be doing. We built the DeepStream SDK for streaming and video analytics to allow developers to focus their efforts on the parts of their application that are specific to their use case and their core intellectual property. It frees developers from having to worry about building the commoditized components for things like decoding, efficient preprocessing, inference, on-screen displays, tiling, and so much more. At its core, the DeepStream SDK lets developers pick and choose from a basket of plugins, weave these plugins together in their code, and build a single application pipeline. And DeepStream 3.0 represents a significant step up in the DeepStream world. There are fundamentally new technologies at your disposal, like a de-warping library that supports 360-degree cameras. There's significant enhancements of existing plugins, massively expanded reference applications, including end-to-end recipes and adaptation guides for building intelligent video analytics applications that go from pixels to insights. And it's all built on the same familiar hardware and software stack, leveraging the NVIDIA ecosystem of tools and technologies like TensorRT, the hardware-based multimedia APIs, the video codec, SDK, as well as offering support for Docker containers and message bus clients like Kafka and MQTT. It is powered by NVIDIA CUDA, and it is one architecture where your application built with DeepStream can run at the edge on Jetson family servers or on Tesla family cards. And as a result, it gives you the freedom to build once and deploy everywhere. So I mentioned that DeepStream 3.0 comes with a reference application, and this is the architecture of one of the reference applications where camera data is coming in through real-time streaming protocol. In this case, it's actually coming from a file source. That data is being captured. And once it's captured, it's being decoded using the NVIDIA hardware-based accelerated decoding built into the GPUs. Then the images are being processed, they're being scaled, they're being dewarped, cropped, also using hardware acceleration. In this case, there are multiple feeds from different cameras that have to be batched together. So stream management is also shown in this reference application about how to take 30 feeds from 30 cameras and analyze them all at once for efficient use of the GPU. And we have multiple neural networks that are run on this reference application. One in particular is run first as a primary neural network, and then secondary models are run depending on what happens in that first neural network. There's also examples of tracking, also leveraging hardware acceleration, visualization, and display on a tiled screen, as well as storage. The reference application architecture gives you a perfect example of what you might need to build for your application. DeepStream 3.0 also has some significant enhancements and new features compared to DeepStream 2.0. It supports the newest Turing architecture GPUs, as well as provides support for TensorRT 5 and CUDA 10, both of which are the most recent releases of these software and driver systems. 3.0 also provides new plugins that provide increased capability as well as increased opportunity for better throughput. One big new feature is dynamic stream management, which allows you to add, remove, or modify your streams on the fly without restarting your application. Now, this provides you both increased flexibility as well as increased stability of your application. We'll touch on that a little bit later. It also provides new plugins that allow you to connect edge to cloud. And these plugins are shown in an example application that comes with the DeepStream 3.0 release, show you how to go all the way from pixels to streaming and batch analytics on the metadata you've extracted that can be analyzed on a cloud server. Because DeepStream 3.0 supports Docker containers, it can be deployed as a set of Dockerized components that allow you to easily scale and manage your application. And DeepStream 3.0 supports Transfer Learning Toolkit model files. The Transfer Learning Toolkit is something we'll touch on in more detail at the end of this webinar. But what this allows you to do is effectively build and adapt pre-trained neural networks to your use case and plug them into a DeepStream application seamlessly. So hopefully now you've got a pretty good sense of what DeepStream is, why it exists, and some of the new features and enhancements in 3.0. We're going to take a step back now and dive a little deeper actually into what powers DeepStream. So DeepStream is an SDK built on top of something called GSTREAMER. GSTREAMER is an open source multimedia analytics framework that is composed of a few core components. At the beginning, there are the concept of plugins. These are the basic building blocks of an application. If you look on the image on the right, you can see that there are plugins that each do a specific thing. For example, plugin 1 is taking data from a source, and perhaps it's doing decoding on that pixel feed. Plugin 2 might be doing things like scaling, and then perhaps sending it off to the next plugin. These are the building blocks that are connected together in an application. Now, something called bins in GSTREAMER and DeepStream is a higher level container that's just a collection of plugins. Multiple plugins come together and achieve some kind of functionality, and that's just what we call a bin. And the pipeline is essentially a bus framework. It's just a top-level bin that provides this bus to manage the synchronization of the application. So GSTREAMER provides several mechanisms for communication and data exchange between the application and the pipeline. So one of them is essentially buffers. Buffers pass streaming data between plugins in the pipeline. You can see in the image on the right, buffers are passing that data from the video file to the decoder, to the scaling plugin, the filter plugin, and then ultimately to a display plugin. Now, events send information between plugins or from the application to the plugin. You can create events for specific use cases. You can also create messages. Now, messages post information on the message bus to be collected by the application. You can also create queries. And queries allow applications to request information from the pipeline explicitly rather than posting it to the application. So with that background on GStreamer, let's take a look at the underlying components of DeepStream. So in DeepStream, the primary building block is the plugin because it's built on the GStreamer framework. It provides a plugin-based model. A graph-based pipeline is created by weaving together these plugins into your application. By interconnecting these plugins together, you benefit from DeepStream's optimized performance for your application. It allows you to leverage heterogeneous processing on the GPU and the CPU. That means that when you use plugins that provide GPU acceleration, as shown in an example on the right, that plugin is going to have access to the low-level NVIDIA optimized library built for that GPU processing, and that data can just be passed along just like it always would be in your pipeline. Now what this does is it hides parallelization and synchronization under the hood. It doesn't force you to worry about that. It does it for you. You can focus on building your custom use case component. And that also means it's inherently multi-threaded. And so by enabling this multi-threaded aspect, the parallelization, heterogeneous processing, your application that you create by taking your plugins, composing your pipeline architecture, is going to be optimized for the NVIDIA GPUs and run effectively on the CPU as well. So why does it run effectively? This is an incredibly important aspect of an intelligent video analytics application, because for many applications, you will either have requirements to operate in either real or near real-time latency, or perhaps you have service level agreements to provide certain latency for specific results. And as a result, efficiently managing memory is critically important. Now, DeepStream provides an optimized data flow that you don't need to worry about. And the way it does this is displayed on this slide. Essentially, what happens when data flows in a DeepStream pipeline is that if you look at on the left of this graphic, you can see that we're looking at the decoding component of a pipeline. In this case, the NV decoding is working on H.264 encoded data. When that data comes in, it's receiving data in the form of an encoded bit stream, either from a file source or a network streaming protocol, whatever it might be. The NV decoding hardware then is used to allocate a pool of output buffers from the GPU in the device memory using the CUDA-malloc API. So we've got a pool of output buffers in the GPU device. Once we've allocated those, the decoder then goes frame by frame and stores that decoded frame into one of the available output buffers. This decoded memory is then shared to all downstream components in the pipeline, such as the NVINFER component for inference, or the NVTracker component for tracking, or perhaps another inference component. But it's not passing the actual data. It's being shared via a buffer pointer enclosed in that GStreamer buffer we talked about earlier. And so what's happening then is at the end of this, after the buffer is consumed by a sync plugin that empties the buffer, and it's returned back to the pool in the beginning for processing and picking up the next frame. So it's not the actual data that's traveling through the pipeline. It's just the pointer that traverses the DeepStream application. And so you end up with a situation in which you have 0 buffer copies in the GPU context. And if you implement a third-party plugin that isn't one of the NVIDIA-created plugins, that's totally fine. As long as it adheres to the DeepStream guidelines, it will automatically ensure that this zero buffer copy memory management process happens when your plugin is being used as well. Now, if the plugin requires you to access data in the CPU context, we will need to make a copy of that data one time. So we'll have to copy that data from the GPU to the CPU using the CUDA memcopy API. And so if you see on this graphic, which is slightly different than the one we saw before, in this case, after the inference component, we are going to be doing some kind of video conversion that's going to require us to do a device-to-host buffer copy. Once we do that, though, we then still get the same zero buffer copy process while we're on the CPU. It's that same mechanism for shared buffers where we pass the pointers once the data is either on the host or the device. This allows you to abstract the need to explicitly manage the memory in your application. You can let the DeepStream SDK handle it for you to allow you to get real-time processing in your intelligent video analytics application. So with memory management just explained, let's now take a closer look at metadata. DeepStream offers an extensible standard structure for metadata that allows you to both benefit from its simplicity, but also expand it if you have more class and metadata requirements in your application. So the DeepStream metadata structure starts at the frame level and has a subset for object level data. Starting from the bottom, you can see that there's a stream ID. In the case of multiple streams, we need to make sure that we identify which streams are associated with which metadata. Now, we also want to track the number of rectangles or number of objects detected in the frame if we're doing object detection. That's what the numRects metadata handles. There's also this thing called the GIE unique ID. This is an individual unique ID assigned to a specific neural network so that if you have multiple neural networks running in your application, metadata generated from them can be separated effectively if you need to do different things with them. Now at the very top, there's that NVDS object parameters, the NVIDIA DeepStream object parameters. This is the subset of metadata information about an object detected in the frame. And for each object that's been detected in the frame, we have the following baseline parameters. Things like bounding box coordinates, label information that might be required for display, such as if you're doing a car detector, what kind of car is it? What is the color of the car? Things like that. There's other attributes of objects that you can define, as well as a tracking ID, which is a unique identifier for that object that has been assigned from the tracking component, and the class identifier, which is the type of object that is assigned based on the results of the neural network itself. So I mentioned that dynamic stream management was a new feature in DeepStream 3.0. This is an important feature because now your application can add or remove streams on the fly, change your FPS, and change resolution, all without restarting the application graph. And so what this really means is that it gives you, as a user, it gives you options. It provides flexibility. But it's also very important because it provides resiliency to your application. For example, if you have a multi-stream application, but you lose one of your streams due to a network disconnect, this will not crash your application. If your resolution is lower due to poor networking conditions from parts of your deployment, application will still work perfectly. All memory allocation and deallocation for this is now handled automatically to allow this kind of dynamic stream management. With DeepStream 3.0, you can also scale out with Docker containers. So over the last few years, there's been a significant rise in the use of containers for deployments. And the reason is pretty simple. Containers encapsulate an application's dependencies to make it reproducible and reliably execute the application without having to spin up an entire virtual machine. And so we've released on NVIDIA GPU Cloud freely available Docker containers that allow you to essentially innovate in minutes and not weeks. It encapsulates everything you need running on top of NVIDIA Docker. And it's also available on Docker Hub. And this will help you get started testing your application rapidly. It makes it super easy to build a heterogeneous application and maintain that application independently. In a few minutes, we're going to go through an example and talk about some of the things you can build with DeepStream and go through some example applications that we've built. Before we do that, though, we're going to do a quick deep dive into a couple of the plugins to give you a sense of what's going on. So the DECODER plugin is the first one I'm going to talk about. IP cameras are one of the more commonly installed cameras in many use cases. And in order to handle these kinds of compressed video streams coming from these cameras, we built a DECODER plugin that leverages the NVDecode low-level API and hardware acceleration that can support multiple streams simultaneously for two of the most popular codecs, H.264, H.265. Both bit depth and resolution will depend on the platform and its underlying hardware capabilities. And this plugin can be connected to other plugins that accept YUV data, such as the inference plugin, video conversion plugins, and more. We also have a batching plugin. The NVIDIA-ACCELERATED plugin allows you to batch data from multiple streams so you can process it efficiently on the GPU. So if you look in this graphic on the left, you can see that there are multiple cameras that need to be decoded. And in this case, perhaps let's imagine there's only 3 cameras, but there could be many, many cameras. The muxer has an internal queue for each connected source. In this case, there's only 3. Each source's output buffer is added to the queue for that source. This happens in that source's output thread. And then the batching algorithm is run. In this case, it's a round-robin algorithm, which really just means it's trying to collect, on average, the same number of frames from each source per batch. And so we're copying the metadata for each frame to the output buffer, since it's going to be necessary later to be aligned. And the batch buffer then gets pushed forward if the batch is full, or it reaches a timeout threshold in which a user is defined a certain amount of time they want to wait and no more for a batch before pushing it through. Now the muxer can only output a single resolution, and so if all input resolutions are the same, everything is fine. You can optionally scale the frames to a user-defined resolution. But if the resolutions are different from different feeds, as a user, you must specify the output resolution. It supports color formats of NB12 and RGBA, and there are no color format conversions. And once that batch is created, it just gets passed off to the downstream components. And one of those downstream components that is likely to be shortly after or right after a batching plugin is the inference plugin, NVINFER. If you look under the hood of this inference plugin, there are many included functions for preprocessing data, things like format conversion, scaling, mean subtraction, and others that allow you to effectively and efficiently leverage accelerated preprocessing in a DeepStream application. Now, this low-level library uses the TensorRT engine, which is NVIDIA's neural network inference optimization framework, to make sure that your neural network is as optimized as possible to run as efficiently as possible. And if it's not supported natively in TensorRT, it allows you to use the iPlugin creator interface for custom layers in TensorRT. And once that model is run, the bounding boxes can be created if you're doing object detection for things like identifying where objects are on a frame or in a frame. And that information can be sent along. Now, 2 things are sent through. The unmodified input buffer is sent through. That is the actual camera data. That's the frame and the metadata associated with that, as well as the new metadata that's been created by the inference plugin. DeepStream 3.0 also has a new library for enabling you to process 360-degree camera feeds. This is a parameterized library that supports converting a fisheye-like image using this new NVWarp360 SDK into different perspectives for different processing requirements. You can go from fisheye to equirectangular, cylindrical, panini, and all sorts of other perspectives. And the transformations are parameterized by the user. The last plugin that I want to highlight is really actually a couple of plugins, but it's a set of 2 plugins that will allow a user to take their perception phase of their application, where you're trying to perceive and create the metadata, extract the information from your video frames and your pixels, and take that and send it off to an analytics server or a cloud backend through a message bus. These 2 plugins, NVIDIA Message Transform and NVIDIA Message Broker, allow you to, out-of-the-box support conversion from your base metadata format in the DeepStream application to a message-based framework and format based on a user-defined schema and specification to go send it off to a Kafka or MQTT-like message bus. I've only gone through a few of them, but there are a host of NVIDIA-accelerated plugins that you can use in a DeepStream application. Now, you can also use non-accelerated plugins in your application because it's built on GSTREAMER. GSTREAMER plugins are at your disposal where you can mix and match to build your application to solve your specific problem set. The NVIDIA accelerated plugins are the ones that we've designed to take advantage in the most optimized way of GPU acceleration. So with that, let's dive into what it means to build an application with DeepStream, and then go through a couple of example applications that we've built. So DeepStream relies on configuration files for your application to run effectively. It tells your application how to handle and how to interact with the environment around it. This is an example of a reference configuration file that you can see if you download the DeepStream SDK. This is only a small subset of the configuration, but the point of this is to show you that the reference application configuration files are highly documented to make sure you can understand what each component of that file is doing. Every parameter is documented both in the actual file itself and in a separate DeepStream documentation PDF that goes into far more detail about what these kinds of configuration parameters are doing. So this is the reference application that's packaged with DeepStream. It is a multi-stream application that shows 30 high-definition streams being processed by 4 deep neural networks running at 30 frames per second. There's a primary network that is detecting whether something is a car or a pedestrian, and then 3 secondary neural networks that are classifying what kind of car or color of car it is if it's a car. That information is then extracted and sent to an on-screen display where it is tiled together. The 30 streams that have been batched in that batching plugin are now separated to create a 30-tile display that allows a user to see the results of this in real time on all the feeds at once.
So this is the reference application that ships with DeepStream. You can see that there are 30 camera streams all being processed in real time by multiple neural networks. You can see that cars are being detected, now people are being detected as bounding boxes are drawn around them. They're being tracked as well. You can see that in this last bit, the people are being obstructed by escalators and more, and they're still being tracked.
So let's take another everyday example. Let's look at a smart parking solution that we built for our headquarters with DeepStream.
So you can see the user interface that we designed. This is our command center UI for our smart parking application. You can see events are being logged when cars move around the system. You can see it's tracking cars by their license plate, and it's also generating alerts. These alerts can be as simple as whether there was a short stay in the parking space or anomalies that were a little more subtle, where there was some kind of unexpected stop where a car was idling in the middle of a thoroughfare in the middle of the parking garage. Now, these kinds of applications are extraordinarily varied. In this case, we now are combining real-time and batch analytics to make heat maps. But what's important is that you can use this as a reference to build any
Let's dive a little bit deeper into that garage application we just saw. This is a visual of the perception graph of this application. The perception graph is just the DeepStream pipeline that handles everything up until we send off that metadata we've created to an analytics server. We can see that, again, a lot of these components are commoditized. We have a communication plugin that's handling the interfacing with the RTSP data stream. We've got pre-processing plugins that are doing things like decoding, leveraging dewarping, calibration. We then have the plugin for detection, classification, and tracking. We're in fact also doing region of interest calibration because of the angle of our camera feed relative to the global positioning that we have for our application. And we're sending that information off to a tracker so we can track the cars in real time. That metadata that we've created then needs to be sent to an analytics server, and we leverage a communication plugin to do that effectively and efficiently. This is why DeepStream is so valuable. It allows us to focus on that inference and intelligence portion and simply leverage the communications plugins, the pre-processing plugins, and more to build our application efficiently and effectively. Now, to really scale this application and make it portable, you can deploy the entire perception and analytics components of your application in containers. You can see on the visual in front of you that we have the DeepStream perception server running, where we have DeepStream applications that are generating metadata. It's being sent off through a message broker, in this case Kafka, to an analytics server and doing things like multi-camera tracking and smoothing with a Python module. There's also anomaly detection and occupancy status being tracked and evaluated with an Apache Spark component. And there's ETL components going on with a Logstash-based approach. That information is then sent through to multiple components, including a state management component that's leveraging Cassandra for persistent storage, as well as an indexer that's based on Elasticsearch, because this is an ELK stack-based application, which then means it's being exposed through an analytics dashboard via Kibana, and there's also an API that you can use for a browser-based application. Now, this entire perception analytics application is fully containerized. Each component is running in its own container. You can spin this up. It is freely available for your evaluation, and you can base your own applications on this. It's on NVIDIA's GitHub. You can also get it through NVIDIA GPU Cloud's Docker registry. I encourage you to check it out. And here we just have a brief still shot of the Command Center UI, the user interface that we saw in that video. You can see that it does things like sensor fusion and is giving you an occupancy map for multiple levels, giving you stats and anomalies and alerts. It's all through a browser-based interface, and you can see this on GitHub. And here's the analytics dashboard that we mentioned in that prior slide. It is a reference dashboard in Kibana to show how all this data can be pulled together for visualization. It's got occupancy and the available spots in the parking garage at any given time. You can see that there's entry and exit traffic patterns over the last 24 hours. There's an anomaly chart over the last 24 hours as well, and a heat map entry-exit showing the periods that are the rush hours. Now, this is just a reference dashboard, but the core message here is that DeepStream 3.0 not only provides the plugins, the optimized components for you to build your perception part of your application, but an end-to-end reference application that you can build with to quickly get up and running, going from pixels to dashboards to business intelligence and to insights. So with that, I'd like to shift gears for the last few minutes to talk about NVIDIA's new product, the Transfer Learning Toolkit. Deep learning is fueling the growth of video analytics applications across the world, and developers are increasingly using deep learning for computer vision-based applications. Public repositories and model zoos have popped up on GitHub and other places, and developers often have two choices when they want to use deep learning in applications. They can use third-party pre-trained models, or they can train a model from scratch. Now, using pre-trained models is popular, but often causes some problems. These models may lack accuracy in the specific use case for this application. They also may be too large. The actual size of the model may pose some issues for some of the more focused embedded deployments. They also might not be optimized for GPUs. On the other side of that, training from scratch, while can be very effective, has drawbacks of its own. Training from scratch can take significant compute resources. It may take significant time to build up enough training data and actually literally spend enough time training from scratch until the model results are accurate enough for production. And it also requires your subject matter experts, or at least your members of your team, to learn the deep learning frameworks like PyTorch, TensorFlow, and others effectively enough to write the code themselves. Having optimized pre-trained deep learning models and a toolkit to tweak them effectively for your use case is the goal. It's the best of both worlds. If you could leverage the third-party pre-trained models so you don't have to train from scratch, but effectively adapt them to your use case, manage and reduce their memory footprint, and optimize them for GPUs. NVIDIA's Transfer Learning Toolkit is a Python-based SDK that allows you and your team to easily do just that. The transfer learning workflow for the IVA use case is simplified with NVIDIA's Transfer Learning Toolkit. Users simply modify configuration files to adapt a model zoo of pre-trained models with their own data. So a user or developer will select a pre-trained model from NVIDIA's model zoo. They will bring their data for their use case or their scene to bear through a configuration file, and the Transfer Learning Toolkit will take care of the rest. It handles pruning, which is the process by which the model is reduced in size while maintaining its accuracy and performance benchmarks to compress that model down. It also handles scene adaptation, all through configuration files. Now, scene adaptation is the process of adapting this existing model to different camera and sensor configurations. The Transfer Learning Toolkit also provides configuration file-based approaches to adding new classes to an existing model. Perhaps if you have a model that's trying to detect Hyundais, Fords, and Toyotas in a parking garage, and now you decide it's important for us to be able to look at Tesla cars, you want to add that class in. The Transfer Learning Toolkit makes it easy to do that. At the end, you end up with an output model that you can pass off to a DeepStream application, just like you would with any other model. It fits right into the inference plugin, and you can accelerate your deep learning training with the Transfer Learning Toolkit and go right into the deployment process in your DeepStream application. So the workflow with DeepStream looks a lot like this. You build your neural networks with the Transfer Learning Toolkit for intelligent video analytics, and you can begin with a pre-trained model, train with new data, adapt it to this scene, and perhaps add classes and prune the models if it's necessary. And then you export that model into the DeepStream application. That is the end-to-end workflow, and NVIDIA is providing SDKs to simplify the process and democratize access to these tools that previously took significant expertise both in the domain and in the neural network and deep learning model training frameworks. Just to go end-to-end even further in the deep learning workflow, you can begin with pre-trained models that then get adapted through a training and adaptation pipeline leveraging the Transfer Learning Toolkit, create a new output model that is then integrated into DeepStream leveraging the inference plugin and TensorRT. The Transfer Learning Toolkit is packaged in a freely available container on NVIDIA GPU Cloud so that users don't have to worry about having all the libraries installed and managing dependencies. You can just download the Docker container from NGC. Deployment is easy and models work seamlessly with DeepStream plugins. And it allows you to accelerate your time to market and save on compute resources because you can get the best of both worlds by leveraging pre-trained models, adapting them to your use case, pruning them to fit more stringent memory requirements if necessary, and quickly getting to market. As a final summary of the Transfer Learning Toolkit, some of the key features that it provides are access to efficient pre-trained models that have been designed to be GPU accelerated from large-scale public data sets, provides access to faster inference by pruning models to reduce their size, which reduces the amount of time it takes to actually run the model, creating faster inference. It allows retraining for scene adaptation and adding new classes by using your custom data and scaling to multiple GPUs with an easy-to-use tool. It also allows you to abstract from having to have deep knowledge on your team of deep learning frameworks by giving you a simple, intuitive interface to these features by managing configuration files. It's fully containerized, and so it's accessible easily from NVIDIA GPU Cloud with all dependencies managed automatically in the container. And it is fully integrated because models are easily consumed through the DeepStream SDK's inference plugin. So I hope you've enjoyed this introduction to DeepStream and NVIDIA's Transfer Learning Toolkit. Whether you're well underway in developing your video analytics application or you're just exploring potential opportunities, the Transfer Learning Toolkit and DeepStream can help you accelerate your IB application from development all the way through deployment. Gives you optimized access to NVIDIA hardware, leveraging NVIDIA-optimized software that goes directly from pre-trained neural network, adapted to your use case, optimized deployment, to a fully integrated application that you can deploy at the edge or in the data center with the same code base. So please visit our website, the DeepStream website, the Transfer Learning Toolkit website are both listed below to learn more about how to download these SDKs, explore our Metropolis platform, and the large ecosystem of software partners that we collaborate with. Please also look at the forums. We will have a brief 10 or 15-minute Q&A session right now, but we may not be able to get to all of your questions. So please go to the forums and interact with our community of developers, both internal to NVIDIA and external, who are working on video analytics applications. And thank you very much for attending the webinar. We'll quickly now go to the Q&A session. Hi, this is Nick Becker. Hope you enjoyed the webinar just now. Thanks for attending. We're going to take the next 10 to 12 minutes to go over some Q&A for everyone based on the questions that you've all been submitting. And please continue to submit questions. We are reading them and we will try to get to them in this time. And if we can't get to them in time, please feel free to reach out to NVIDIA on the developer forums, and we'll try to get back to you as soon as possible. So one question that has come up many times is, how do I actually download DeepStream? I want to start developing applications, but I don't know where to get this. So you can download DeepStream from the NVIDIA website. It's free to download, and we encourage you to get started by checking out the documentation that comes with DeepStream, as well as additional documentation you can download from the website. If you are familiar with Docker containers, we highly recommend and encourage you to look at the DeepStream Docker containers in the NVIDIA GPU Cloud registry. These are containers designed to help you get up and running quickly. They have the DeepStream binaries you need, as well as all the other requirements and dependencies packaged up into a clear container to help you spin up as fast as possible. One other question that's related to this, that many of you have wondered, is, can I run the same application that I build with DeepStream on Jetson and Tesla GPUs? And the answer to that is yes. Yes, you can. the same DeepStream application can be deployed on both Jetson and Tesla lines, giving you a truly scalable architecture. Another question that's been coming up several times is, I don't have a Tesla or Jetson platform GPU. Can I still use DeepStream? So we only do quality assurance and testing on Tesla and Jetson platforms, but you're welcome to try DeepStream applications with GPUs of any family as long as the architecture is a Pascal or more recent architecture, and we expect it to work. But I want to reiterate that we do only test and do quality assurance on Tesla and Jetson-based platforms. Another question that's come up several times is, how does this work in terms of memory management with the Jetson Xavier? So DeepStream 3.0 was recently released for Jetson Xavier, and because of the unified memory between the CPU and GPU, you have an additional benefit of not needing to copy data between the GPU and the CPU if aspects of your pipeline require different components to run on the host and on the device. And a question that a few of you have asked is, do I have to compile each separate component of a DeepStream application? Can a single application be compiled once, or do I have to do each single plugin compiled and weave it together and orchestrate that whole thing? The answer is no. A DeepStream pipeline is a single application that you build in your code, and you compile it once as a complete application. In the examples we went through in the webinar, we saw how you could take a DeepStream pipeline and extract metadata and insight and information from a video feed, and then pass off that metadata to an analytics backend, to a larger system that is going to accomplish a much broader business intelligence or decision layer-based goal. If you want to build a larger system, you would need to build additional system components to handle that kind of work, like we saw in the Smart Garage example, and we saw in detail in that reference architecture where different components were running in different containers. Now, these would be separate components, and so if need be, they would need to be compiled separately. To aid in that kind of process and helping you and giving you a baseline from which you can start thinking about how to build these kinds of end-to-end insight applications, we provide an example playbook of how you can do this exact thing. It's available via GitHub in the NVIDIA AI-IoT repository, as well as in the DeepStream Docker containers on NVIDIA GPU Cloud. And you can spin up these Docker containers or download the code from the GitHub repository and check out exactly how this application works and use that as a launch pad for your own application. Another question that we've gotten this, and we just touched on this, but I want to reiterate, is that this software is free. Both DeepStream and the Transfer Learning Toolkit are free SDKs that NVIDIA has released to help you build and deploy intelligent video analytics and intelligent applications in general more effectively. Another question that a few of you have asked is about Transfer Learning Toolkit. Transfer Learning Toolkit is designed to output a TensorRT runtime engine, a TensorRT plan file. This can be seamlessly integrated into DeepStream, but it's a TensorRT run file, which means it can be used in any application that can support TensorRT. And TensorRT, for those who might not be quite as familiar, is a programmable inference accelerator designed to allow you to optimize already trained neural networks to have the highest throughput at the lowest latency. Another question that a few of you, or a couple of you have asked, is about whether or not DeepStream has a built-in component or plugin for things like tracking and other things. I mentioned in the webinar that DeepStream ships with reference examples. One of the reference examples uses a tracking component that's built into DeepStream as one of the plugins. Now, you can use this plugin in any application you want, but I encourage you to look at the reference applications to see how the tracking component is being used. In this case, it is designed into the metadata, as we saw, where the ID coming from that tracking component is part of that extensible metadata structure that you can grab that that's flowing attached to the buffer in the DeepStream application. Another question that we saw, and this is a great question, it's pretty general, which is, what are some preferred resources for DeepStream tutorials? It's a great question. We've released several containers that help you get up and running with DeepStream, and they have those because they have the DeepStream binaries. They also have the reference applications they ship with. But we also highly encourage you to look at the NVIDIA developer blog. The NVIDIA developer blog has several examples of how you can understand at the code level and at the product level how to really get started using DeepStream, both in conjunction with Transfer Learning Toolkit and without Transfer Learning Toolkit if you already have an optimized model. Another place that I highly recommend you look at is the NVIDIA developer forums. I mentioned it in the final slide of the presentation, but the DeepStream and the Jetson forums and on the NVIDIA developer zone are both highly active, where NVIDIA internal staff as well as community developers can interact and talk about what they're building, and the questions they have can be discussed by the entire community. It's a great resource and highly encourage you to check it out. Another question is whether or not the Transfer Learning Toolkit is something that is part of the DeepStream application itself. The Transfer Learning Toolkit is an additional SDK. It's another SDK released by NVIDIA. So as a result, it doesn't ship with DeepStream. If you download if you spin up the DeepStream container and then you are looking for the Transfer Learning Toolkit, it's not currently part of that container. In the same way, if you spin up the Transfer Learning Toolkit container, or if you download Transfer Learning Toolkit through the Early Access program and then you spin this up, it doesn't ship with DeepStream. However, as we mentioned, these are designed as a first-class citizen to be used seamlessly together. There's another question about what the actual stack is that we recommend for running these kinds of applications. We've released an example application for our Smart Garage, and we've made some design choices that worked for this application. And we hope that it inspires other developers to base their own application on that if it's relevant. Ultimately, the right message broker, whether it's Kafka and MQTT or something else, is going to depend on the requirements and specifics of your specific application, your service level requirements, and that's going to be something that ultimately you have to decide. We encourage you, though, to look at how we built this application. There's in the GitHub repository I mentioned a few minutes ago, it's documented that shows what each component is, or what each section of the analytics backend is doing, and we encourage you to check it out. One last question, because of the interest of time, is what kind of frame rate are you getting with the HD video running on the Jetson Xavier? I believe this question is specifically referencing the reference architecture that comes with DeepStream that we were just showing in one of the slides. That application is running 30 HD videos, and they're being processed by that exact reference application with the 4 neural networks, and it's running at 30 FPS. I think it's running at 30.1 or 30.2 FPS. DeepStream on Xavier is an extremely powerful tool because Xavier supports 3 different power levels depending on what kinds of requirements you need. As a result, it allows you to, in the 30 watt and the 15 watt power mode, to be able to get that kind of real-time processing you need despite having that highly compute-intensive intelligence layer. And with that, it's about 2 o'clock. Thank you all for coming. It's the last question that we will take today.
Thanks, everybody, for attending today's webinar, and thank you, Nick, for presenting. There were a lot of questions towards the end that we weren't able to get to, so please be sure to post those on the forum to keep the conversation going. We've recorded this presentation, and we'll have it, along with the slides, available shortly on demand. You'll also receive an email with a link to this information. And don't forget to become an NVIDIA registered developer to get access to the latest news on products, software, events, and more. Thanks for joining us, and have a great day, guys.